Hey guys, welcome. Thank you for joining. This is the Oracle Autonomous Database Learning Lounge. I'm Marcos Enosibia, part of the product management team for Autonomous Database. And today we have a very cool session on Graph. So how to actually use Graph to find patterns in your data, right? And so we're going to do this session with Melliyal Annamalai. She's a great colleague of mine, very experienced with Graph, working for many years with these technologies. And she's going to talk about how to use Graph and find these new insights in your data with Autonomous Database. Okay. So Melliyal Annamalai, she's a distinguished product manager. She's going to be explaining to you guys how modeling your data as a graph, right, can help you find connections in the data. So she's going to be talking about all the ways that graphs can be used, giving specific industry examples, and also talk about the Graph Studio, which is actually an exclusive component of the Autonomous Database, and how you can create and model graphs right there directly, right, using notebooks in the Autonomous Database. And then it's going to talk about the examples of, for example, finding fraud, right, with graphs. So throughout the session, we have product managers available. So Dr. Jayant Sharma is on call here. Hans Wienman is on call. I have Marty Gubar. So any questions you guys have, at any time, make sure to type them in the Q&A. Okay. So there's a Q&A for Zoom. You type your question there, and we're going to make sure that we get back to you. Okay. We're going to also post some links in chat, and the recording is going to be made available, by the end of the week. Okay. So to begin with, I just wanted to show you guys, if you are not familiar with Autonomous Database or have any questions about it or have not seen this before, these are just several links that are the most important links to have handy for Autonomous Database. I'm going to put them in right now in the chat. So I'm pasting them in the chat for you guys, so you guys have that information handy, right? So Melli, thank you very much for joining us again early on your time. Really appreciate it. I'm going to stop sharing, and then I'll let you share your screen. And again, thank you very much, and you have a great audience.
Thank you very much, Marcos. That was a very nice welcome. So very warm welcome to everyone. It's really great that you could join us here today to learn about graphs, and specifically how we've made it easy to get started with graphs when you're using Autonomous Database. So given that I think vast majority of you are not familiar with graphs, it's, I think, appropriate that I start with what are graphs and why they're interesting today when it comes to finding new insights in your data. So you can think of graphs as a data model that helps you make explicit the connections that exist in your data. Our data always has these connections, and an obvious example is a social network, where if I repost someone's message, that's a connection between me and that person. If I follow someone on a social media network, that's a connection between me and that person, and so on. So connections are kind of natural in any social network. They're less maybe obvious in bank transactions. For example, if I go out to dinner with my friend and then I transfer some money using a payment solutions app, that's a connection between my bank account and my friend's bank account, because money was transferred from one account to another. So similarly, there are connections in any data set that you look at, and the graph data model helps you make these connections explicit so that you can then run queries based on these connections to find patterns, like how these connections form patterns in your data. You can run algorithms from graph theory to get new insights into your data, and we will be looking at all those examples here today. So I'll just use a quote from one of our customers who is a Paysafe, is a payment solutions company. And for them, graphs really allowed them to dig a little deeper into the data and get insights from their data to understand how these transactions were going on, was there any fraud in the transactions and so on. They're able to do this because they model their data as a graph. It was more straightforward to find out how the cash transfer flow and what that meant for their business. So graph. So I'm going to assume that everyone is familiar with the relational model where you organize data as rows and columns in tables. So if you want to ask, if you have a table here and you want to ask the question, is A connected to B? We can say that A and B are in the same row, so they have a relationship that perhaps A depends on B. And then B depends on C, and that's a relationship between B and C. If you want to ask the question, is A dependent on F? If you were to do this with a relational table, you would perhaps run some queries with self-joins that then find out that whether A is connected to F or not. When you model the same data as a graph, and what we do in Autonomous Database is help you create a graph view on this data. When you have this graph view of this data, it becomes easier to ask this question. There's a syntax in the querying to ask the question, is A connected to F? And it's not directly connected to F, it's connected to F via D and E. And that becomes obvious, or it's more easy to express in a graph query. So the graph data model makes it more intuitive to see these connections. So moving on to other examples of patterns that we might look for when we are modeling our data as a graph is, let's say you have this account I here, and you can say, I want to look at the number of incoming connections to node I. Like in the payment solutions example, this would be, which are the accounts or how many accounts are directly transferring money to node I. And from this model, you can see that there are 3 direct connections to node I. But what graphs are particularly good at is also finding the indirect connections. Like E and F are not directly connected to I, but they're connected to I through G, and F is connected to I in 2 ways, through G and through H. So again, if you're looking at financial transfers, you can see here that E transfers some money to G perhaps, G transfers money to I, so there is a connection between E and I. So graphs are really good at finding connections, and especially finding these connections when you don't know necessarily the length of that path or the number of hops in that path. You just want to say, is there a path between E and I? I think graphs are really good at answering such questions. So here we have this extending on their theme. We say, okay, C is about 4 hops away, so you can keep finding the number of incoming connections to node I. And we can ask questions, is A directly connected to C? No, A is not directly connected to C, but it is indirectly connected to C via node B. So the graph data model just lets you follow or traverse these connections. So let's now look at an example with data. So kind of helps you kind of make some of these concepts concrete. So let's say we have in our autonomous database 2 tables, the bank accounts table and the bank transactions table. The bank accounts table has information about the accounts, such as the account ID, the name of the account holder, perhaps their address, phone number, and things like that. And the bank transactions table contains information about which account transferred money to which account. So all the cash transfer information is captured in this table. So we're going to see how we're going to take these 2 tables and create a graph from it to answer questions such as this. So when you're uncovering fraud, and these questions are the questions customers like Paysafe are trying to answer. Are there unusual cash transfer patterns? For example, if money is moving around in cycles, like if A transfers money to B and B transfers money to C, C transfers money back to A, that is a unusual pattern in their business. So banks are often very interested in knowing whether money is moving around in cycles. So for that, you need to traverse the connections. And again, the graph model makes it easy for you to do that. And perhaps there has been an account identified as might be engaged in fraudulent activities. Which other accounts are connected to that account either directly or indirectly? then which are the accounts that have a lot of money flowing through them? And this might be a valid thing that's happening. Like if it's a utility company's account, lots of people who subscribe to the utility are just transferring their monthly payments to that account. But depending on the business, that might be something suspicious. If it's a money laundering scheme or something, you might want to see. You might want to identify accounts that have lots of money flowing through it. So that's a pattern. And which pairs of accounts have an unusually high number of cash transactions happening between them. So we're going to see how we will model the two tables as a graph so you can answer some of these questions. So first, a little bit about the graph data model, or specifically the property graph data model. So in a relational model, data is organized as rows and columns. And in the property graph model, we have what is known as vertices, which are essentially the entities in your data. So anything in your data, like an account is a thing, customer, product, these are all things in your data, entities in your data, and they naturally become vertices. And any relationship between these entities is an edge. Like in the bank example, it would be an account transferring money to another account. The transfer is a relationship between the two accounts. If your vertices are customers and products, when a customer buys a product, that's the relationship between them, the relationship being buy, and that's an edge between the two entities. So in any data set, there is a relationship between entities based on how they're interacting with each other, and that becomes the edge in the graph. And then you have more information about these vertices and edges. For accounts, you have account name, you have address and phone number. These become the properties for the vertices. And similarly, there are properties for the edges. Like if you're doing a transfer between two accounts, what's the amount that is transferred, what's the date of transfer, and so on. Hence the name, the property graph data model. So it's the same data, just organized a little differently so that we can ask queries a little differently. So I've added some data here to the two tables, the bank accounts table and the bank transactions table. So when you're using autonomous database, you can just select the tables and say, I want to create a graph. So, and I'll be showing this in the demo, but first the screenshot looks something like this. I'm saying, okay, I have all of these tables in the graph user schema. I'm selecting these two sets of, these two tables here, and I want to say create a graph. That it's as simple as that. So what happens when you're doing that in autonomous database, we look at the primary key information, we look at any foreign key relationships between the columns in the tables, and then we suggest a graph model for you, saying that this is the graph model that fits these tables, that fits how these tables could potentially interact with each other. So here's the proposed graph model. You can then change it if you wish, or you can just use the graph, you can customize it, or you can use the graph model as is. So the autonomous database makes it really easy to create this graph. You could basically get started very easily with any set of tables that you have. So let's look at what happens behind the scenes. So I have here the accounts, and the accounts are the things in my data. So every account is a vertex. So every row in this bank accounts table becomes a vertex in the graph, because that's going to be the entities that I have in my data. And every time I have a relationship between two of these entities, like a transfer from account ID 1 to account ID 672, that is the transfer relationship, and that is an edge in the graph. So here I have another row here that there's a transfer relationship between account 2 and account 833, and that's another edge in the graph. So what happens behind the scenes is this is identified as the vertex table, and this is identified as the edge table. And the graph is created. Well, so what happens when the graph is created is we create some metadata tables to capture this information, so that when you query the graph, we know how the data is connected, and we're able to execute the query. So here is what the automated modeler will generate. and execute to create the graph. You have this create property graph, and you're listing the vertex tables, which as we saw was a bank accounts table, and then the edge tables, which is the bank transactions table. So in this example, for simplicity, I only have 2 tables, but you can have any number of tables. In fact, we have a customer who is just about soon going to go into production, and they're creating that graph from nearly 400 tables. So any set of tables that you have, you can create a graph from the table. And note that this is a graph view of your data. And what that means is you can use this graph with operational workloads. Like many vendors, when they are working with graphs, they'll say you have to copy this data into a specialized schema or into a separate database altogether because you have to work with the data as a graph. What we have is a graph view. So you can continue your DML operations on the underlying tables, and all of that is instantly reflected in the graph. So that's a pretty powerful feature. So when you create this graph, you either manually or either programmatically or from using the automated modeler, you would get a graph that looks like this. Visually, we can represent the graph like this, where you have vertices representing accounts and edges representing the transfer relationship between them. And then we can ask the business questions that we have. Which are the highly connected accounts? You can see here visually, it's easy to see that there are highly connected accounts. And we'll see some examples of how we would ask queries to get the same answer. Are there cycles starting with this account and starting and ending with this account? And then are there paths? So I've identified 681 as maybe a suspicious account. Is there a path between 681 and 228, either directly or indirectly? And are there accounts which are not very highly connected? Here, for example, is an account that only has one incoming transactions. I want to know whether there are accounts which don't have a lot of transactions. So again, these are all how you're connecting your accounts and asking queries based on those connections. So now let's look at some query examples. So I want to reinforce once again that we are creating a graph view over tables in Autonomous Database. There was no data copy, data that's remained in the Autonomous Database tables, and when they're queried as a graph. And now we come to the actual queries. So when you have this graph model, you need the syntax to specify this pattern. Like you need the syntax to specify a cycle or the syntax to specify a path. And that's what any graph query language will allow you to do. So here you can see the line in blue is the match clause, which specifies the pattern. Anything in parentheses is a vertex, is a variable representing a vertex. So you have A here as the source. You have A here as another vertex, the destination here, and then you have 1, 2, 3 here in curly braces. So what this is basically saying is start from A and ending with A, so ending with the same account, but I want to find parts that are 1 to 3 hops long. So when I'm starting and ending with the same account, that's a cycle. So are there cycles 1 to 3 hops long when the account ID is 259? That's basically what this query is asking. So now coming to the language. So in 23, we have been working with the SQL Standards Committee to add the syntax to SQL, and it is part of the standard SQL 2023 that was recently published, and we plan to include this in Oracle Database 23c. So in Oracle Database 23c, you'll be able to use this kind of syntax in SQL. But we have had this graph feature since 12.2. So if you have a 19c database, for instance, and you want to run graph queries, you can use the PGQL language, the property graph query language, which is pretty much identical to the SQL syntax because we were participating in the standard. We are familiar with what the syntax is going to be. And we implemented the property graph query language to be very similar to the SQL syntax. So if you're using 19c, you'd use the property graph query language, and we worked hard to ensure that the property graph query language is compatible with SQL tools. For instance, in SQL Developer, you can have a PGQL worksheet where you can create a property graph, you can run PGQL queries. SQL CL has a PGQL plugin. If you're developing applications in Java or Python, you have the ability to have a connection over which you can send PGQL queries to the database. And of course, in 23C, all of this is going to be in SQL, so it'll become even more simple. We also have a graph visualization tool that allows you to submit graph queries, and then you can go to the, which will be submitted to the database. As you will see with the Graph Studio in Autonomous Database, the visualization is integrated with Notebook. So let's switch over to an Autonomous Database console here so that we can run some of these queries. So you can see here that this is in database actions, you have this Graph Studio card, and that's how you click on to open Graph Studio. And I have various things I can do. I have graphs I can look at. I have notebooks I can look at. So let me go to, let me actually go to this page here, where this is the graph page. So if I want to create a graph, I was showing you some screenshots. So I could, just to show again how this works, I already have created this graph. So I'm not going to fully go through all the steps, but I just want to give you a feeling for how simple this is to create a graph from your tables. I have all of these tables here. I can select two tables. And once I select these two tables, I can say, okay, now I want to create a graph. And this is when the modeler is looking at the schema and determining it is automatically identified that this is a vertex table and this is an edge table. And you have the source here. You can look at the source to create property graph. You can change it if you want to. And then you can click on next to go ahead and create the graph. But since I have already created a graph, I'm just going to switch to the notebooks here and actually have this notebook open here. So let me just switch on to this tab here. So I have this notebook, which allows you to run many different, which has many different interpreters. It has a Python interpreter, it's a SQL interpreter. It also allows you to run Java snippets and PGQL, which is what we'll be running now. So you can run graph queries in this notebook, and they're going to be executed in Graph Studio. And I should have mentioned, Graph Studio is a feature of Autonomous Database. So any Autonomous Database you provision, Graph Studio is available for you. So here is a simple PGQL query where you say I'm just saying select edges and limit by 100. So it's like saying select star from tab. I just want to select a few edges. So when I run this, I'm going to select a few edges from this graph. And here's the graph that I have here. It's retrieved the results from the database and is visualizing this in Notebook. It looks similar to what we were looking at in the slides. I could customize this with any other layout if I wanted. We have interesting features when it comes to visualization and so on. So let me look at another query. See, this query, and let's focus on the match clause here. So the match clause, it now says starting with account A and ending with account A. So that's again looking for cycles. And I'm saying 1 to 5 hops long, and I'm given here as an argument account 534. So you can see here that I said 1 to 5 hops long. So this is 3 hops long, and account a cycle starting and ending with 534. So the match any gives you one cycle. You also could have a match all, like find me all cycles. And, but this is match any, and we'll look at that example in a second. So here in this query now, I'm going to use these built-in functions to say, find me the in degree and out degree, the number of incoming and outgoing transactions for vertices, and I'm using the order by to order them. So you can see here that 934 has a high number of incoming and outgoing transactions, as does 387. So if I'm looking for fraud, these are, and if I feel that the high number of transactions is suspicious, then these are two accounts that I maybe need to dig a little deeper into them to see what is going on with these accounts. what other patterns can I find that involve these accounts. So here I'm going to say, okay, I'm going to start with account 934, and I'm again looking for cycles, like I'm starting and ending with the same variable here. And then I'm going to say, find me exactly 4-hop cycles. Because I have reason to believe that 4-hop cycles mean something. So, okay, tell me exactly 4-hop cycles. So on here, you can see the syntax is match all. Not so match any is find any one cycle, match all is find all cycles. So here I find all cycles that are exactly 4 hops long that start and end with account 934. So here I'm going to ask a different query. I'm going to go to 5 hops, exactly 5 hops, and otherwise I'm doing the same match all again. So find me all cycles that are 5 hops long, and then this is interesting. So when I said 5, I suddenly got a lot more cycles than I had when I had 4. So if somebody is involved in some kind of money laundering, which is when you see one example, when you see money moving around in cycles, they are going to look for longer and longer cycles where possible. So it's interesting that I have many more cycles here when I use 5 hops rather than 4 hops. So now I had seen that 934 and 387 were the account with the top numbers, with high numbers of incoming and outgoing transactions. So let me see whether there's a path between them. So I want to find the shortest path between these two accounts. Well, A is 934 and B is 387. And here I'm using the plus syntax, which tells me just find me one or more hops. Find me all paths. So this is not a cycle. Find me all paths one or more hops long between 934 and 387. I'm also saying find me the shortest path. So there might be any number of paths. So I'm saying find me the shortest path, and the shortest path is 4 here, or other, I should say 3. So yeah, so there is a path between 934 and 387. And here I can, I'm just modifying the query a little bit to say match top 3 shortest paths. So I'm just not looking at the shortest paths, I'm looking at the top 3 shortest paths. And you can see here that you have 387, you have 934. So there are 3 paths here. There's one here, there's one here, and then there's another path here. So 3 shortest paths. And then finally, top 5 shortest paths. So you can keep finding information about how your accounts are connected, which in this case represents how money is flowing between these accounts. So now let me go back to the slides to look at property graph analytics, which is another category of operations you can use with your graph when you're modeling your data as a graph. So with queries, we were looking at paths. We are saying, okay, how is I connected? How many indirect connections? How many direct connections? And things like that. Is there a path between 2 accounts? With graph analytics, you are basically looking at the entire graph to look at how everything is connected together. And let me illustrate this here. So let's say to this graph model, we have added 3 new accounts, J, K, and L. Each one of them is connected by one edge to the existing graph. But J also has is connected by one edge to the existing graph, but that connection comes from node I, which has a lot of incoming connections. So that makes J more interesting than L and K because it's connected to a highly connected node. Like in social media, this could be that if you're connected to an influencer, that makes you important. You're only one hop away from an influencer, and so on. So PageRank algorithm is really good for identifying the importance of such nodes, not just by looking at the number of connections that a node has, but whether a node or vertex is connected to such a highly connected node. So that's an example of a graph analytics algorithm. And we have, as part of Autonomous Database, over 60 pre-built algorithms that you can invoke either through a Java or a Python API. So here you have different categories. For example, you have finding the components. That would be finding highly connected subcomponents within the graph, like finding communities that are connected to each other, finding important nodes, that's PageRank, that and the category of algorithms there, finding parts, machine learning, where you can combine graphs to enhance machine learning models, provide additional input to machine learning models, and so on. So many different categories of algorithms. So let's see what new questions we can ask of this graph after asking now that we can do graph analytics on this graph. So the key thing you can ask is, are there accounts that are connected to highly connected accounts? So you see here 967 might not be highly connected, but it is connected to a highly connected account. And similarly, 102 and 581 are connected to a highly connected account. So when you run the PageRank algorithm, every vertex will get a value between 0 and 1. And higher the value, more likely it is that they're connected to other highly connected accounts. So in this case, 967, 102, and 581 will have a higher PageRank score. 569 will probably have a lower PageRank score. So an algorithm like PageRank goes through the entire graph and recursively evaluates how the entities are connected, and then comes up with a score that it assigns to each vertex. So because our algorithms are pre-built, this is a simple API call to invoke on your graph. You can do PageRank. We have personalized PageRank, which is a modified version of PageRank where you're not looking at the whole graph, but you're looking at the relative score of a vertex as it relates to a particular vertex or set of vertices in the graph. You're finding the number of hops, the shortest hop distance that any vertex is connected to a given vertex, and so on. So there are many different algorithms that you just invoke using a simple API call. So let me go back to our notebook to basically run the PageRank algorithm here. So you see here, I'm going to run the PageRank algorithm, and I'm running this on this graph. And Graph Studio includes a graph server that is designed to run graph algorithms at very high speeds. So once I run this algorithm, I said every vertex will have a score between 0 and 1. And this becomes a property of the vertex in the graph. And I can now query the graph based on this property. I can say select account ID and select the PageRank value for a graph for the vertices, and I'm ordering here by PageRank value. So I see here the values between 0 and 1, and I see here 387 as a high PageRank value. It also had a high number of transactions incoming and outgoing. But 934 has been pushed down the list, and a 406 has emerged as something with a high PageRank value. So though 406 is not highly connected itself, it has a high PageRank value. So now I can use that information in visualizing this graph. So if I'm I can use the PageRank value to visualize the results of a query. So here I am saying, find me, I'm starting with account 934, and I'm saying, find me all paths that are 6 hops long, and 934 is a high PageRank value, and I can see the accounts in the path that have a high PageRank value. It's just the visualization capabilities in Notebook. And here I am comparing the PageRank order with the number of transactions order. So we have the PageRank value, like I said, 387 is in both lists, but here 934 is down the list here, and 406 is not even listed. So PageRank gives you a more complex and more sophisticated measure of identifying vertices that are highly connected, or kind of evaluating how connected a vertex is. So here's again an example of personalized PageRank, where you are finding the relative importance or relative connectedness of a vertex as related to 2 specific vertices in the graph. Here I'm choosing 934 and 387, and I'm saying I want to find I want to see how connected they are in relationship with these 2 vertices. And then I get a PageRank value, and then again, I'm querying by this personalized PageRank value, is again a value between 0 and 1. And once again, here 387 and 934 are high naturally because they are part of the vertices that you're comparing with. Then 406 comes up again as a highly connected vertex. So it's highly connected as it relates to these two accounts. So and so on. You can I can then run a query for 406 because I want to see other accounts that 406 is connected to, because 406 has emerged as something that I need to explore further, and then I can do so here. So, and we can go on, there are more algorithms, and this is available as part of a live lab, so you can run a few more algorithms there. So let me go back to my presentation here, and let's talk about one example. One other example, just to give you a sense for how we would create a graph from a different set of tables. So if we have a set of tables, let's say a customer and information about which movies a customer has watched. So you have a table of customers, you have a table of movies, and you have a table connecting the customer table with the movie table, which has information on which customer watched which movie, whichever title is watched here. So if this is a movie stream company, you would have information on which customer watched which movie. And going back to graph modeling, the customers are the natural things or entities in your data, as other movies. So you have customers as vertices. You also have movies as vertices. So you have two types of vertices in this graph. And the relationship between them is watched. So once again, any data set that you have, there will be some relationship between them. And you have this watched relationship between the customer vertex and the movie vertex. So the customer table and the movie table are the vertex tables, and the watch table is the edge table. So if you can create a graph from this table, again, create a graph view. And then you can run an algorithm on this graph to identify what movies to recommend to a particular customer. Here, this snippet shows the personalized salsa algorithm, which is going to assign a score to movies based on how movies are connected to the different customers and based on the viewing pattern. So you have Emilio connected to different movies here. You have Floyd also connected to different movies. So based on how these movies are connected to different customers and based on whether there's an overlap in the movies these customers watch, these movies get a score. And higher the score, better the recommendation for Emilio. So if there are movies that at the high score that Emilio has not yet watched, that's a good recommendation for Emilio. So it's all about looking at how data is connected and determining the movies to recommend based on those connections. And for example, Emilio has watched this movie many, many times, and that will factor into like how many edges do you have between this customer and this movie. That factors into this algorithm as well. So that leads me to talking a little bit about other customer examples with graph. So another example from a financial services company, this is Kesha Bank, where they are modeling their customers as vertices in the graph. And every time they identify a relationship between these customers, they make that an edge in the graph. For example, if two customers swipe their credit cards at the same eating establishment, they assume, they think that maybe these are two customers having lunch together. So they add an edge between them because there is a connection or some relationship between these two customers. So this is something they might not have derived from other information because they might not be family members, they might not be colleagues, they just happen to be friends having lunch together. So they identify the relationship and they keep building up the graph by adding edges every time they identify a relationship between their customers. And then they run the graph clustering algorithms to identify tightly connected clusters, like which of these customers have a lot of relationships with each other and with other members in the group, which gives me an idea that maybe these are customers with similar income levels, similar interests, so I can better tailor product recommendations to them. And in manufacturing, this is an example where you have where they wanted to create a digital thread connecting all the components that are used together. So there are, of course, hundreds and thousands of components, and components are the same component is used in many different products, like many different cars might have the same component. They might also be used by trucks. In a large manufacturing company where they're manufacturing many products, these components could be used in multiple products. So they wanted to make explicit those connections to identify what they call is to create a digital thread among all the components that have some connections based on whether they're used together, based on whether a component is made of other subcomponents. And with this graph view of this data, how these components are linked together, they're able to then run algorithms to say, if this is a component with a high PageRank value, perhaps it is used in a lot of products that we make. And if components are clustered together, maybe these components are used together in a lot of the products we make. So the ability to traverse these cross-domain links gave them all kinds of interesting insights into the data. And graphs have applications across the board: financial services, manufacturing, healthcare, finding patient communities, transportation, telecommunications, where you can analyze network topologies to identify vulnerabilities, or if there is an outage, you can have a what if analysis. You could have done an what if analysis to say which are the components that would be, which are the vertices that would be impacted, by looking at which are reachable from a particular path, or doing root cause analysis. So when there's an outage, you have signals coming in from various different components, but I want to go to the source, and that's like a path analysis. I want to find out the source that triggered all of these signals so that I can more effectively go to that source and address the problem. So graphs have applicability in many different domains. So anytime you have data, your data will have connections, either implicit or explicit, and graphs have a role to play. And you can do all kinds of interesting things. And autonomous database makes it really easy for you to get started with graphs. You have a table, you create a graph, and then you have this notebook that you can use to just start querying. When you're building applications, you can connect to it using a graph with client libraries and so on. So the key takeaways is that Graph Studio and Autonomous Database makes it really easy, particularly with an automated modeling of tools and integrated visualization. And we now, if you want to try it today with Autonomous Database, you'll be using the PGQL graph query language. But when 23C is available, you will be using SQL. You can use SQL. And it comes with over 60 pre-built graph algorithms to do all kinds of interesting things with your data viewed through a graph data model. And of course, all of this is available with all the enterprise database features that we have. So here are some resources to get started. The example that I was showing here is available as a live lab. So you can try and run through the exact same example. The data is available. You'll be able to do exactly what I was doing. It's very simple. It's a lab that doesn't really take more than 30 to 40 minutes. And we have a YouTube channel where we post interesting videos. We also have a blog both on oracle.com and also on Medium. So I hope you enjoyed this session, and let's see now whether there are any questions that we should answer live.
Excellent. Thank you very much, Melli. It was a great session. We had a lot of great questions. I see questions still coming. Okay, guys, so keep the questions coming. I see already a few other questions coming in. That's great. So in the meantime, just some final thoughts here. You got, again, a few of the links there. And to go and come back and see the recording and also check the slides, right, that Melli shared, you guys can just come back to the ADB Learning Lounge, and you're going to see the links there. So there are links there. The next sessions are going to be listed there. And when you're going to each session, you're going to have links to the slides as well, and the video recording on YouTube. Okay. And I think for now, that's it. Again, Q&A is still open. So I'm going to leave this running. In the meantime, thank you for joining today. We have upcoming sessions are going to be maps and apps. So we're going to be talking about the Oracle Spatial and Autonomous Database. We're going to have a multi-cloud integration with Autonomous Database. And we have a hands-on workshop with data sharing. These are the next sessions. You guys are going to see them in the calendar there for Ask Tom. Okay? All right. With that, again, thank you very much, Melli. Really appreciate you joining us today. I'm going to, again, leave this running. So I'm going to fade out to music, but I'm going to leave this running. In the meantime, you guys can still ask questions, and we're going to still be here. All right?
Thank you very much, Marcos.
Thank you very much. Really appreciate it. Thank you, guys. And thank you, Giant, and thank you, Hans, for all the questions that have been answered as well while Melli was presenting. Really appreciate it, guys.